In section 2 of chapter 20, we're going to go ahead and look at how to actually balance redox reactions. Okay, and we're going to look at them initially from the acidic perspective, and then we're going to progress into the basic. So the first thing that we need to understand is that we're going to have to take our reaction, whatever it is, and separate it into our half reactions. So we've established those skills from the previous section 1, and so we're going to basically just apply some of those same principles. We'll worry about the number of electrons later, but for right now we just need to figure out what is our reactant and product for each step. So in this case, we have Fe2 plus to Fe3 plus. We know that an oxidation has occurred because it's become more positive, so we're going to draw our half reaction this way. And then same process, we're going to figure out, using the skills that we've obtained, that we have a plus 6 oxidation number on our chromium, followed by a plus 3. That's an obvious reduction, so we know that these are our half reduction, or excuse me, our half reaction pieces. The next step is to balance the other atoms in the half reactions other than hydrogen and oxygen. Okay, so we don't need to worry about that for the oxidation step because iron and iron, there's only one of each type of element on both sides of the arrow. But for the chromate and the chromium 3 plus, we do need to do some balancing. So notice you have 2 chromiums in this chromate anion. So we're going to go ahead and put a coefficient of 2 in front of the Cr3 plus. Okay, so now that we've balanced all the other atoms except for oxygen, we're then going to proceed with balancing the oxygen atoms. So we're going to balance the oxygen atoms in acidic reactions with H2O. So notice on this side we have 7 oxygens. Okay, so we're going to give ourselves 7 H2Os on the other side. Okay, and since we've done that, we can then now balance the H's. Okay, so we're going to do that by using H+. So if we look down here, we're going to balance the 14 H's that we just added on with 14 H pluses on that left-hand side. Okay, we don't need to do this for the oxidation portion, the iron to iron, because as we said earlier, there were no other atoms present, so there was no stress there. Okay, well let's go ahead and look at step 4. The next thing we do in this step 4 is we're going to add electrons to each side of the half reaction to balance the charges that are present. Okay, so Fe2 plus gives me Fe3 plus. So 3 plus 1 minus is going to give me plus 2. So by adding 1 electron, I balance the charges on both sides. Okay, and on the reduction side of things, okay, I'm going to have to get an overall plus 6 on this right-hand side. So let's go ahead and look at what we have. We have a minus 2. We have a minus, sorry, we have a plus, we have a plus 14. Okay, so 14 minus 2 is 12. Minus 6 is going to give me an overall charge of plus 6. And with that being said, now we've established the correct number of electrons on each side. Now we have to look at the half reactions as if we're going to be combining them. So in step number 5, what we're going to do is we're going to multiply the half reactions so that the number of electrons in both the oxidation and reduction half reactions match. Okay, so in this case, obviously, we initially started with a 1 electron here, okay, but we needed to multiply through by 6 in order to balance with the 6 electrons that we saw in the reducing step. So if we go ahead and continue, what we're going to do is then add the half reactions together and balance the final equation. And we're going to look at this. So initially what we have here is we have 6 electrons and 6 electrons. Those are definitely going to cancel each other. Okay, iron doesn't balance or doesn't cancel out, neither does hydrogen or chromate or chromium 3 plus or water. So what we do then is we bring each of the things that are remaining down, okay, for both your reactants and product side. Okay, after we've done that, we need to verify that the number of atoms and the charges are sufficiently balanced. Okay, so if we look at this, okay, we have our charges that we're going to look at. So 14 times 1, okay, that's coming from our H+. Our chromate, there's only one ion there, which is -2. And then we have 6 2+ charged ions. That gives us 24. So on the left-hand side, we have an overall charge of 24. Excuse me, plus 24. Okay, on the right-hand side, we need to have that same setup. So the oxygen doesn't, or the H2O doesn't contribute anything, so we can ignore there. But we do have 2 times 3 plus chromates. Okay, and then 6 times 3 plus irons. Okay, so 18 plus 6 is going to give us a total of 24. So our charge is definitely balanced. Okay, you also, though, have to make sure that all the elements match. Or, excuse me, you have to make sure that all the elements are also balanced. So let's not forget to do that. So let's look at this. Okay, I got 2 times 7 hydrogens. That's 14 hydrogens. I have 14 hydrogens on this side. I have 2 chromiums. I have 2 chromiums on the left. I have 6 irons. I have 6 irons on both sides. Okay, so we've done the balancing based on the fact that we now have an equal number of elements on the left and right hand side, and we have the correct number of charges on both sides. So, with that being said, that's the basic acidic balancing procedure. But there are extra steps that you'll need to take with basic solutions. And with a basic solution, what you're going to do is you're going to add hydroxide ions to both sides for every equation that has H+. We're going to go ahead and look through a couple of examples there, but you just basically follow the same steps except for the hydroxide addition. So let's go ahead and let's look at the balancing of the reduction or the redox reaction under basic conditions. Okay, so we have this following equation here, and we're going to still follow the same steps that we've done before. The first thing we're going to do is write our half reactions. Okay, notice that we have a manganese ion that went from +7 to +4. Okay, so that's a reduction. Okay, and our carbon atom, okay, it went from +2 to +3 here. Okay, so we have now our oxidation steps. So we've written our 2 half reactions. Okay, so then our next step, of course, is to make sure that all of our elements besides oxygen and hydrogen are balanced. And if we look at the first 2, we have 1 manganese on the left, 1 manganese on the right. Okay, and we have 1 carbon and 1 nitrogen on the left, and 1 carbon and 1 nitrogen on the right in the oxidation half reaction. So we've done step 1 and 2 here. Now, step number 3, what we're going to be looking at is, of course, balancing our oxygens. Okay, so notice that on the left-hand side here, we have 4 oxygens. We have 2 coming from our manganese oxide. So we're going to add 2 waters in order to balance the oxygens present. Okay, we're going to do the same thing with our oxidation half reaction. Okay, and in this case, we have a single oxygen on the right-hand side, so we're going to add a single H2O molecule on the left. Okay, and then continuing with step 3, we're going to now counterbalance the hydrogens present. Okay, so we added 2 H2Os here, so now we have 4 H2Os. So we need to add 4 H pluses on the left-hand side. Similarly, we added 1 H2O on the left-hand side here. That gives us 2 H's on the left, so now we need to put 2 H's on the right. So now our 4th step is going to entail us balancing our charges. So notice over here on the right-hand side, we have 2 neutral molecules, so we have an overall charge of 0. If we look at the left-hand side, though, we have -1, we have 4 plus 1s. Okay, so in order to get neutral, or to a neutral state, just like the right-hand side, we're going to have to add 3 electrons. Okay, similarly, if we look down at the bottom, notice that we have a single -1 charge on the left-hand side. Okay, so in order to get that to happen, okay, we're going to have to add 2 electrons to counterbalance the 2 H pluses and the -1. Okay, so we have a -1 charge on the left, -1 charge on the right, and so now things are balanced. Now, if we continue on, then what we do is we try to counterbalance, or balance out the number of electrons in both the oxidation and reduction step. Okay, in this case we had 3 electrons and 2 electrons. So in order to make those work out, we're going to multiply the reduction half reaction by 2, as you can see here, and everything gets multiplied through by 2. And then the oxidation step we're going to multiply through by 3. Okay, so once we've gotten those two multiplied all the way out, what we're then going to do is we're going to sum our two reactions. So when we go ahead and we sum our two reactions, now when we sum our two reactions, what we're going to do is we're going to cancel out the things that overlap. So 6 electrons on the left, 6 electrons on the right, those are going to nicely cancel. We have 3 H2Os on the left, 4 H2Os on the right, so that's going to leave us with a single H2O over here. Okay. Our H pluses, we have 6 H pluses on the right, we have 8 on the left, so that's going to leave us with 2 H plus. Okay, and then what you do is you go ahead and you carry down each of the remaining species. So as you can see, right, we have each of these remaining. Okay, and they come down. Okay, same thing with everything that's on the right hand side. Okay, everything that remains, it comes down. Okay, and then since this is a basic reaction, what we then have to do is we have to add hydroxide ions in order to counterbalance the H pluses present. So we know that we only have one H plus left over, or sorry, 2 H pluses left over, so we're going to add 2 OH minuses. And we're going to do that to both sides. So notice I added 2 OHs on the left-hand side, 2 OHs on the right-hand side. Okay, and then what I do is I combine them. So anytime there's a H plus present, and I've added OH minus to that side, I need to combine them to create waters. Okay, so I rewrite the equation as the combined water and the hydroxide with everything else, and then what I'm going to do is I'm going to cancel out anything that overlaps. So once again, I have 2 H2Os on this side. Okay, I have 1 H2O over here, so that's going to become 1 H2O, and then I bring down all the remaining items. Okay, everything comes down. Okay, and your last step, guys, is the same step that you would have done if this is an acidic setup. Okay, I have it written as step 7, but obviously those are inverted when it's a basic situation. Is you're going to count the number of atoms and make sure that that all balances, and you're going to count the number of charges on each side. Okay, so hydrogens, I have 2 hydrogens here. I have 2 hydrogens there. Okay, manganese, I have 2 of them. 2 of them. Carbon, I have 3 and 3. It's good. Okay, nitrogen, 3, 3. Okay, I have those balanced. Oxygen, okay, I have 8, 9 on this side. Okay, oxygen, I have 3, 4, 5, 6, 7, 8, 9 on the right hand side. Okay, so all of my elements add up. So the last thing I need to check are my charges. Okay, so I have 2 permanganates, so that's -2, plus 3 cyanide anions. Okay, so that gives me a total of -5. I have a total of -5 on the left-hand side. Okay, and I have that same total on the right-hand side. Okay, so I have balanced this equation in basic solution using these specific steps. And you guys are going to use these steps to do all the rest of your balancing for the remainder of this unit. So why do I even care about redox reactions? Like, what's the point of even breaking these down? Yes, this happens, magic, who cares? Well, the reality of it is you should care. Why? Because when electrons move from location to location, that's actually an electromotive force, or something that can actually provide a usable source of energy. So, when we've looked at our example so far, we've looked at reactions that are in the same container, right? So we've put copper 2+ ions and zinc solid in the same place, and we've watched a reaction occur, but there's not been really any actual useful work done. Okay, so separating these reactions is going to be what allows us to monopolize on the fact that electrons are moving from one thing to another, and then that's the natural course. And that's going to bring us into our next section, in which we'll talk about cell potentials. But for now, what we want to understand is that the half reactions, how to write them, how to balance them in acidic and basic conditions, and of course understanding that the movement of these electrons is actually going to be useful for work.